So now we're going to go through some of the derivative rules. So remind me, what's a derivative? So hopefully what you said or can chant to yourself, because you want to know all the words. The derivative is an operation that yields a function that tells you the slope of the original function at every point in its domain. Okay? So derivative is an operation. It's something that's going to transform the function to reveal new meaning about the original function. That's the key idea, right? But let's also not lose sight of the fact that the derivative is to find slope. And what's slope? Slope is just a ratio of changes. So it's also an operation that yields a function that describes how the function's value changes at a specific point in the domain, right? So two notions there. But we're going to be a bit more practical with our derivative. So just to go over a couple of notation things again, just so that we've got this. If I have a function f of x, its derivative is going to be noted as f prime of x. Okay, that's one notion there. If we've got f of x, and I want to talk about this as a derivative, remember the derivative operator is d dx, which means that I get d f of x dx. Sometimes that's a little awkward, so I can talk about d dx of y, and then I get dy dx, right? And I can write it like this, or I can write it like that. This notion shows it very nicely as the derivative is an operator. It's the thing that acts on this. This shows it very nicely as ratios of change, because this literally says a little change in x compared to a little change in y, and their ratio because of the division there. Okay, so just that notation just to remind us of a couple of things. So a couple of rules then to go over. Let's say I have a very simple one, d dx of x, right? So let's say the function is f of x equals x, right? Well, what does that look like? Well, this is showing it in terms of it's an operator acting on x. But if I just look at this in its other notation, looking at it as a ratio, I think that's pretty obvious then, because I have a little change in x and a little change of x. What's that ratio? Well, that ratio is always 1. Okay, so our first derivative rule, d dx of x is equal to 1. Now, kind of a corollary to that, if I've got d dx of, say, a constant, c being a constant, right? C equals a constant. Well, what's that going to be? Well, that says, how does the constant change as I change x? It doesn't, right? So there is no change in the constant as I change values of x through the domain. Now we can kind of put some of these things together and start talking about then what happens if I have d dx and the function is c times x. Well, remember, that's just saying like the line y equals x has a different slope, right? And since we know this thing is the slope, notice here c is the slope, so it should make sense that this is c, okay? So there we go. Boom. So there's some easy little derivative rules we could talk about. Oh, by the way, another way to write this, just so we can look at this, is I can imagine that this is the same thing as pulling out the constant as if the operation of the derivative with respect to x never touched this. And I'm going to show another way to get to this answer here. We get the same idea in a couple of minutes. Right? So those are some of the basic derivative rules. Anything that I have boxed is like a formal derivative rule. So the first thing that we're going to talk is about major thing is something called the sum rule. So let's say I have a function that's actually made of two functions. So let's say that my original composite here, I keep saying composite, the original conglomeration, I guess is a better way of saying it, is like g of x plus f of x if I have two functions, okay? Now that could just be as simple of g of x is x and f of x is 2, right? Any polynomial is really just the sum of a bunch of simpler functions. Now, keep that in mind. So what we're going to say is that if I were to apply the derivative operator to this, so d dx applied to the whole thing, what we're going to find out here is that the derivative operator simply distributes across addition. Okay, well, why is that? Well, let's put this in a real world context. Not really a real world context, but those of you studying for the ACT and SAT may have seen examples of something like this. Like you have two ditch diggers. Ditch digger A can dig 5 feet of ditch per hour, and ditch digger B can dig 8 feet of ditch per hour, right? How much ditch do ditch diggers A and B dig together if they're to dig simultaneously? Well, if you think about it, both of these things are ratios, right? And specifically they're rates. That if you have this guy who can do 5 feet per hour and this woman who can do 8 feet per hour, if they're working together, they can do obviously 13 feet per hour, right? There you go. I mean, unless they're fighting or whatnot, there's some sort of social interdynamic that we don't know about. But let's leave that aside. But that's just the basic logic here, that I had two functions and their derivatives just added together. So two ratios that added together, right? But notice that they were both, in this case, they are both, this would probably be g of t and f of t, and this would be d dt and d dt, because we're talking about over time. But there you go. That's the sort of internal logic of the sum rule, is that how each function changes is added together so you know how the combination of the two functions change. Awesome. The next thing we want to talk about is something called the product rule, and that's what happens if I have g of x and f of x, right, multiplied together. Now, let's talk about a common function that we know that is the product of two other things. So, for example, the area function. Area is length times width. So there we go. Okay? Now, what I want to talk about here is how does the area change when I change these parameters, right? And so one way to talk about that, let's say let's say the length and width are changing over time. That means that the area is changing over time. So my goal here is to find how does the area change over time, okay? Now, let's say I change the length, right? So let's just define our terms length and width. So let's say I change the length. We're going to do this a bit more finitely and not talk about what's going on in these little small amounts of time. But let's say I change the length by a certain amount, delta L. Now notice there, delta L. That's a large change in L. Let's just go back and define terms there. Delta L was a large change in L, but dL would be an infinitesimally small change in L. Remember that this is called a differential, right? And this is called just a change, right? A finite change, an infinitesimal change. So this shaded in area here would be the large change in A, not a dA, because I have a delta L, I get a delta A. How large is delta A? Well, delta A is just very simply how much the length changed by times the width. Boom. So there you have it. Now, what's going on instead if I change the width, right, without changing the length? So there we go. I changed the width by a certain amount, and that's delta W, right? And so now here's my delta A, and there's my L. So now my delta A is equal to the length times the change in width. Makes sense there, right? Well, what happens now if I change both the length and the width simultaneously, right? So what I've got to do here is I've got to add on this sort of L-shaped thing. So there's the change in length, and there's the change in width. So what I want you to do is stop the video for a second and come up with a change in A. All right, cool. So hopefully you got that. There's a lot of ways to do this, folks. I think the easiest way to do this, break this up into 3 areas. Here's the original length, here's the original width. So if you notice here, this amount here I'll call delta A1, this is delta A2, and this is delta A3. So delta A1 is just the length times the change in width. Delta A2 is just plus the width times the change in length, right? And then finally, I have delta L times delta W, which is the area of this box here. Now, here's where things get magical. What happens here if I'm changing, but rather than I'm doing these large changes, I'm doing just these really small changes, right? So these things were all being changed over time, okay? So I can just put that common ratio of delta t on the bottom. What happens here if I take the limit as delta t goes to 0, the amount of time over which the change occurs gets really small. Well, what happens here is this doesn't become dA dt, or rather delta A over delta t, it becomes dA over dt. In a really small change in time, I get a really small change in area. Well, what happens to the first term? Well, I get L times dW dt. And the second term becomes W times dL dt. But something weird happens here. Notice here I have a large quantity, L, times a small quantity, dW. Here, a large quantity times a small quantity. Here, I would almost end up with like a dL times a dW. These two things are so small that when you multiply two really small things together, they actually just vanish. Look graphically here. If I shrink this little wedge down here and shrink this box gets smaller faster than each of these boxes getting smaller. And there you have, at the end of the day, what the answer is. So going back to what this looks like, if my original function then was A equals L times W, and I end up with dA dt was L dW dt plus W dL dt, right? We can expand that outwards and just say, if I take the derivative with respect to, say, x of f of x times g of x, I end up with, if you look at this, I take the first function, L, right, times the derivative of the second function, so that's the derivative of g of x, plus the second function times the derivative of the first. And that's the way I want you to think of it. First times derivative of the second, plus second times derivative of the first. And that's how you do, this is what's called the product rule. So I'm going to do that. Now, one last rule for this video, and then we'll have a bunch of practice, right? Let's think of the simplest product that you know. Going back to our original example, let's say that our function, I don't know, f of x is equal to c times x. Well, technically, that's the product of c times x. Let's use our new product rule to see what happens there. Well, I get the derivative of f of x in this case with respect to x is the first function, c, times the derivative of the second function, so the derivative of x with respect to x, plus the second function, x, times the derivative of the first, which is c. Now we know from our original rules that the derivative of a constant is 0, and this is the identity, so that's 1, and so I get c. So the derivative of cx with respect to x is equal to c. That was actually one of our rules from before. Technically it was grounded in the product rule, but we kind of used other means to do it. Let's talk about some other rules, or not other rules, but other applications of this. Well, if I had f of x is equal to x squared, technically x squared is x times x. So if I take the derivative of both sides with respect to x, let's follow the pattern. So the derivative of x squared with respect to x is equal to the first function x times the derivative of the second, plus the second function, which is x, times the derivative of the first, which is x. Notice I get the identity there, and there you go. I end up with 2x. So the derivative of x squared is, with respect to x, is 2x. Now that's not a rule, so I won't box that. That's an example. So let's go to now another function. Let's say y is equal to x cubed. Well, what's x cubed? Well, x cubed is x squared, which we have the answer for here, times x. So let's use that. So if I take the derivative of that with respect to x, dy dx, or another way to say that is dx cubed. Dx in this case is the first function, x squared, times the derivative of the second, so that's the derivative of x with respect to x, plus the second function, x, times the derivative of the first. Boom. So here we go. That's the identity. So the first term becomes x squared, the second term is x times, and we know the derivative of x squared with respect to x, we just got it up there, is 2x, and so I've got x squared plus 2x squared. Oh, I've got 3x squared, and I got it. Once again, I'm not boxing that, that's an example. Let's do one more. Let's say y is equal to x to the fourth. Now, I could split that up in a bunch of different ways. I could say x cubed times x, or x times x cubed. I'm just going to do x squared times x squared because it's just the simplest, so we have some parallelism there. So the derivative of x to the fourth, or dy, dx, whatever you want to choose to say, is the first function times the derivative of the second, plus the second function, times the derivative of the first. Now these two terms are identical, so I'm just going to combine them before I do anything, right? And then we already know the derivative of x squared with respect to x is 2x. And so there you go, I have 4x cubed. So hopefully now you've seen a pattern. So I'm going to stop the video for a second and see if you see a pattern. All right, hopefully what you've seen is in each of these cases that if I take the derivative with respect to x of x to some variable n, I've gotten kind of a similar thing in each case. When I had the derivative of x squared, I ended up with 2x. With x cubed, it was 3x squared. X to the fourth, 4x cubed. So what are we doing in each case? Well, it looks like in each case what's happening here is the original function is being multiplied by its previous exponent times x to the 1 less power. Box it. This is known as the power rule. And it's a really, really great tool that allows us to shortcut a whole bunch of steps rather than having to do all these product rules over and over again, right? And so what I want you to do is sometime between now and the next time we talk, think about why would the derivative of x to some power always be a function to the 1 less power, right? So I want you to think about that. And so from here, I want you to realize that we can now do any polynomial function, right? So if I've got this, then I can do x to the 7th plus 4x squared plus 3x minus 2, because first all I would do here is the sum rule, and then for each of the terms, I can then just use I can use the product rule, I can deal with the fact that it has coefficients. I've got all that stuff down. what we're going to look at the next video is what happens when when the functions look a little bit messier. For example, what happens if I've got, say, for example, 4x to the 5th plus 7, and you're like, oh, well, I could do that. That's easy, to the 10th. Now it's no longer easy because it doesn't fit into this form because it's not x to the n, it's some function to the n. And that's going to be the focus of our next video, is how to deal with this problem.